this is joint work with Pierre, Louis, and Effie on, on data integration and trade-offs. So I'm going to describe the problem that we work on first informally with an example, and then go into our formalization. That would be most of the talk. And then I'll just give a flavor of our results, doing the easiest results, but hopefully encouraging you to look at the paper. So in data integration, we have a bunch of sources. Each source has a local schema, this I sub s. And the full set of schema over all sources is what we call a D schema or distributed schema. And you can use the same notation for instances. You have local instances and D instances. And the trade-off problem we want to look at is data owners are interested in making some data available, views of their data available, so that particular queries that we call utility queries become answerable. I'll explain how that's formalized in a bit. At the same time, they have some inexpressiveness limitation. They want to reveal as little as possible is one limitation we look at. And the second is that they have a finer grained notion where they have some secret queries that they don't want to disclose. And the trade-off problem is there a mechanism, a set of views that's useful, but doesn't reveal too much? So the running toy example is going to be Ezra and Diego. Ezra, as we all know, has a spicy database of KR reviews. And Diego, through some clever hacking, has a similar database for Jachiet 2020. And they want to collaborate to support queries that are legitimate for the community to know, like, was there some reviewer who reviewed a paper by the same author in both conferences? And here I've written out that utility query in logic. And at the same time, well, the way they're going to do it is export data from their local sources, and then a third party should be able to reconstruct the answer to this query from their data. At the same time, they don't want to reveal too much. Maybe they have some specific information, like whether Mantis reviewed a paper by Yasmin that they don't want to reveal. So if you look at this particular example, you will see that, okay, they could do it using cryptography. And maybe in the Q&A, I'll mention something about how this is done classically. But if they want to use traditional database views, it's looking very difficult for them. So let's start with the formalization. We'll look at general views, which are just functions on a local source, outputting data in any output schema. And if we have one of these sets of views on every local source, looking only at data at the local sources and deriving some output data, together these form what we'll call a distributed view or D view. So this is a very general notion of view, but I emphasize in the slide that this is a deterministic notion. It's a function that I would assume, when I'm talking about non-disclosure, that all the third parties and all the attackers would know. And this is different from what happens in the privacy algorithms literature, where they mostly consider mechanisms which are about injecting random noise. We model these things always deterministically. And these are non-interactive mechanisms, and that's just to emphasize, Diego and Ezra just give out some data and that's it, as opposed to the mechanisms you see in the privacy literature, which involve multi-round protocols between the sources that are probabilistic. So we'll often impose definability restrictions. That's one of the main novelties, which is we'll look at the case where the views are traditional database queries, conjunctive queries, existential quantifications of conjunctions. Every view is over its local source. So in the example, Ezra might export the authors who reviewed in KR from her local source. It won't be useful in satisfying the utility query that I mentioned, but she could do that. That's a legitimate conjunctive query view. What does it mean for these queries, utility queries, to be answerable? Well, we use determinacy as a general notion of answerability. It's a very general notion of rewritability. Some views, let's say a D view, determines a utility query if any two global instances, any two D instances that agree on all the views agree on the utility query. And we'll always identify usefulness with determinacy. And I think it's easiest to explain this in terms of a picture. Determinacy says there's some sort of reconstruction function on the output space, the image of the views, such that if I compose that reconstruction function with the views, I always get the query answer. So it says that a third party using some function can reconstruct the query result from the view images. And you might worry that this is really general notion of rewriting, and this is requiring the third party to do some crazy reconstruction function. But it will turn out that this makes our negative results about Diego and Ezra much stronger, because it says, you know, they can't support this utility query in a certain way with any reconstruction function. And for our positive results, we'll always use very simple reconstruction functions like joins. So here's an example with Ezra and Diego. Ezra could export the KR authors and KR reviewers in isolation, two separate views without the correlation. And this won't be useful regardless about what Diego exports, just because we've lost the correlation. On the other hand, you know, Ezra and Diego could both export the author-reviewer combinations. And this is clearly useful. The reconstruction function is just a join to reconstruct the query result. But of course, they're giving away the store when they do this. So we can get an idea of the trade-offs involved just looking at this. So what does it mean that a mechanism doesn't reveal too much, the inexpressiveness requirement? Well, we say a D-view is minimally informative useful within a class of queries. If it's useful, it's based on the queries in C. They'll generally be, say, CQ queries. And for any other D-view that's useful and uses those queries, that view V prime determines each view in V. And the intuition is V prime determines each view in V means I can reconstruct V from V prime, so V prime has more information than V. And this says any other thing that's useful has more information, or at least as much information. So again, we're using determinacy as a partial order on information in views. What does it mean that the views don't disclose a set of queries? Well, we have a very general notion of a non-disclosure function. It's a black box that says this view discloses this query. And we only require that this function is determinacy compatible. That is, if V discloses something and V prime determines each view in V, which means V prime has at least as much information as V, then V prime should always disclose P. Any reasonable disclosure function you could think of is determinacy compatible. In the paper, we often work in our examples at least, and in the last section with a particular non-disclosure function. In this talk, this won't be important. There are many disclosure functions that you could consider. So a simple proposition is minimally informative useful D-views, when they exist, are minimal in terms of the secret queries that they disclose. So if you have minimally informative useful D-views, those are the ones you want to look at to see if they satisfy a trade-off. If they don't work, nothing will work. So going back to Ezra and Diego to talk about disclosure, if I look at this secret query, say in a KR context that Mantas reviewed a paper by Yasmin. Here it is as a secret query. And suppose Ezra exports the reviewers and authors only of paper 100. Intuitively, this is disclosing for the secret query because Yasmin might have written paper 100, and then Yasmin and Mantas might be returned, in which case the game is up. Everyone knows that Mantas reviewed the paper by Yasmin. But it depends on the non-disclosure function. If you have a strong notion of disclosure that says a third party can find out the answer on every database, then this is okay. But if you have another notion of disclosure that says the third party can sometimes find out the answer to the query, then this is not okay. Okay, in the paper, we'll always look at CQ utility queries and secret queries only. We also consider a variation of the problem with background knowledge. These definitions all have straightforward relativizations to sources satisfying the background. And here is a brief overview of our results. We show that minimally informative useful D views exist if we restrict to CQ views. And this result extends in the presence of background knowledge in the form of existential rules. If those rules are all local to a source, each rule mentions only the stuff in each source. And then we show that minimally informative useful views also exist within the class of all queries, but they're not always CQ based. So basically you can do more trade-offs with relational algebra views or with general views than with CQ views. And I think this is one of the more interesting results in the paper. And these results also extend to local rules. And then we look at the simplest kind of non-local knowledge, constraints that say that a certain relation is replicated between two sources. And there we show that minimally informative useful views don't always exist, but we can still, under some additional hypothesis on the utility query, get D views that minimize the set of secret queries that are disclosing. Okay, I can't tell you about all these results, but I'll say a little bit about one of the simplest results, the first one. Given a distributed schema and a CQ the canonical D view of Q is the D view where on source S, you give away one view whose body is all the atoms on that source, and the output variables are all the variables that cross sources in the utility query. And so it's easy to show this by the Diego Ezra example. Here was my utility query. And what Ezra exports in the canonical view is just the atom over her source, but with paper ID 1 projected out because it's not shared with the other source. Diego does a similar thing. He exports a CQ with the atom for his source and projecting out the variable that isn't shared. This is the canonical D view. Intuitively, this should be the minimal information thing to support this utility query. It's clear that this is not very private, as we said before. The theorem says that if the utility query is a minimal CQ, that is, it has no redundant atoms, then the canonical D view is minimally informative useful among the set of all CQ views, which is just what you'd expect intuitively. And therefore, if anything is going to work that's CQ based and is useful, then the canonical D view works. And using this, you can show that Ezra and Diego are out of luck using CQ views. We have a generalization of canonical views for general views along with a corresponding theorem. And using that, you can show that Diego and Ezra are out of luck even if they want to use general views. The generalization is a bit more technical. I want to point out this theorem isn't true if minimality is dropped. We have a counterexample. If we consider all views rather than CQ views, it's not the canonical view, D view, that's the thing that works. It's something a little bit more complicated using some ideas about symmetries of the queries. If we have background knowledge that's non-Horn or crosses sources, this theorem isn't true and the story becomes more complicated. So to wrap up, we revisit problems that were really revisited with certain twists in the privacy and algorithms community, these trade-off problems. The kind of tools that we give, because our formalization is very different based on deterministic functions, the techniques appear to be totally different from what you see in that literature. We show definability restrictions have an impact, CQ versus arbitrary views, which I think is what's interesting for KR. We show that the kind of background knowledge that you have has a big impact as well. Thank you for your attention.